So last time we were discussing that atoms follow this offer principle, that they have different subshells, and the electronic configuration is written according to the subshell, the arrangement of these subshells. The 1, 2, 3, 4, etc. These numbers, they indicate energy levels, which means that or principal quantum numbers or shell numbers. What they represent is that if the energy is low, if the number is low, that means the electron would be very close to the nucleus. It would be the negative charge would be located close to the nucleus. If the number is bigger, that means the negative charge would be located much further away, because the electron is energetic and it would overcome the attractive force of the nucleus, and the electron would be buzzing around in spaces much further away. And so you had this arrangement, and all atoms would follow that. So neon had 10 electrons, so it's going to be 1s2, 2s2, and 2p6. 2p has so 1s2 is this small, s is the spherical subshell. So the 2 electrons would be located in this spherical area over here. They would be very low energy, because that's 1. That means the energy is really low. So the electrons would be sticking close to the nucleus. The negative charge of the electrons would be very close to the nucleus. Then you have 2 electrons in the 2s. That means the 2 electrons that are also located, they're buzzing around in a spherical region around the nucleus, but those 2 electrons are kind of are more energetic, which means they would be much further away from the nucleus. And then you have the 2p. The 2p has a different shape, and it's got 3 different types of p. So there's 2px, which means that the 2 electrons, the negative charge would be distributed or spread around the x-axis in 2 lobes. So the electrons would be buzzing around in this space over here. There would be 2 electrons in the y area, y-axis. So that's 2py, and there would be 2 electrons in the 2pz region over here. So that's electronic configuration of neon. This is how a neon atom actually looks like. You wouldn't be asked to draw all of the subshells in one go. That you'll be asked in your exams to draw any one specific subshell, because it's harder to draw all of them together. So iron, we did the same thing. So you can just follow the arrows and from the top to the bottom, and you'll be able to figure out the electronic configuration. One thing that I told you yesterday was that you should arrange, once the electronic configuration is written, you should, I mean, it's preferable, the convention is that you should group them according to energy levels. So it's better to group subshells or rearrange them according to energy levels. So that will give you an idea that which electron is the furthest away from the nucleus. So if the energy level is 4, keep it really far away. That's because the electron is going to be very far away. If the energy level is 1, it should be closest to the nucleus. So arrange them according to it. The 1 subshell should come together, 2 subshells should come together. So it's better to write them according to the energy levels. And then we discussed that we discussed one minor thing, and that was that how do 2 electrons exist in the same orbital or the same space? Why do each orbital, they always have 2 electrons? And the reason was that the 2 electrons, they repel each other. So initially, it's very hard for them to actually stay together. But I also explained that electrons are not just negative charge. They also have an accompanying magnetic field. So whenever you think of electrons, you always use the term electromagnetic, which means they have magnetism as well. So you should think of them from now on as tiny magnets as well. And these arrows, they kind of represent the north and south poles of those tiny magnets. So electrons are not just negative charge. There's another way of thinking about electrons, and that is to think of them as tiny magnets. And when you think of them as tiny magnets, magnets can repel and magnets can attract each other. So if the magnets and their poles, their north and south poles, are opposite to each other, they're going to attract each other. So which is why the 2 electrons are able to overcome the force of repulsion Why? Because the magnetic poles, the magnetic dipoles, the north and south poles, in chemistry terms, that's known as magnetic spin. Otherwise, it's got nothing to do with the word spin. It's just a terminology that is used. Whenever you see the term magnetic spin, that's just north and south pole. So opposite magnetic fields will attract. So electrons, if they are in the same orbital, they would always have opposite magnetic fields, opposite magnetic dipoles, which is why they're able to overcome the force of repulsion. Now, another thing,
Sir,
yes.
this doesn't mean that they actually stick together though, right?
It doesn't mean that they start to actually attract each other, because they're also repelling each other. So it's basically just kind of canceling the force of repulsion.
Yeah, so they're just like neutral, like they're not attracting nor are they repelling.
Yeah. Actually, they're still kind of repelling. I mean, the force of repulsion is still kind of greater than the force of attraction that is created by the magnetic field.
Okay.
And also remember that I mean, it's kind of forces. Like I told you that generally on in the universe there are three main forces. I mean most of the macro, not the quantum level, but at the macro scale, there are three forces that are kind of governing everything. That's gravity, there's magnetic force, and there's electrostatic force, right? Chemistry deals with electrostatic force. It's all about protons and neutrons all attracting each other, all types of bonding, chemical bonding, ionic bonding. It's all electrostatic force. In physics, you study magnetic force. So the thing is that that different forces have different kind of strengths. So it's not that the two forces are kind of similar. The repulsion is still kind of stronger. So the electrons are still kind of repelling each other, but now they're kind of repelling each other with a lot less force, because some of the repulsion is getting cancelled out. Is that clear?
Yes, sir.
And now well, there's one more thing that needs to be discussed about electronic configuration. Two more things, actually. One is how to fill an incomplete subshell. So how to fill an incomplete subshell. Do inform me if you can't see the writing on the screen, like if it's too small. Just a second, I've lost the port. So 1 second. So how to fill an incomplete subshell. So I mean, if the subshell is full, that's not an issue. Like all the orbitals are going to have 2 electrons each. But let's say if I have a nitrogen atom, nitrogen has a total of 7 electrons. Like if you follow the Aufbau principle, it's going to be 1s2, followed by 2s2, and the last one would be 2p. The 2p is supposed to have 6 electrons. Like it's got 3 orbitals, 2px, 2py, and 2pz, but you're running out of electrons. So there would be just 3 electrons instead of the 6 electrons. So what does that mean? What that means is, and we're focusing on this, like it's got these 3 orbitals, the 2px, 2py, and 2pz. So there are many different ways in which those 3 electrons can be filled. Sorry, the subshell can be filled. There could either be 2 electrons in one of the orbitals, and maybe 1 electron left in the other orbital, or so there could be many different arrangements. The arrangement that is going to happen is that initially, because the subshells, the orbitals are exactly identical. Remember, when you talk about the 2p, I mean, this is the 2p this is what the 2p subshell looks like. It's got 3 different orbitals, and they're all identical. They have zero difference between them. So for an electron, they're all exactly the same. The px, the py, pz, the only difference is the direction. Now remember, the electron doesn't know which one is the x-axis or which one is the y-axis and which one is the z-axis. Remember this, that the x, y, and z are arbitrary axes. Like if you have your room, it's you who's deciding which one is the x and which one is the y and which one is the z. So it's all relative. It's you can assign any axis the x-axis. So the point is they're all identical. So for an electron, they all look exactly the same. So if you put them together, this is what a 2p subshell looks like. The electron could be on the z-axis. Sorry, let's call this the y-axis. The electron could be on the x-axis, or the electron could be buzzing around on the z-axis. So how would 3 electrons occupy this subshell? So what they're going to do is, initially the electrons prefer to occupy each orbital in a subshell in a single manner first. So one electron would go into each of those orbitals. Why would that happen? The reason that would happen is that the electrons are going to prefer this way, because in this way they can avoid repulsion. So let's assume that this is the nucleus, and here are the 3 axes. You can label any one the x-axis, y-axis, or z-axis. So let's call this the x, this one the y, and this one the z-axis. Think of this in 3 dimensions. I mean, think of the drawing in 3 dimensions. So you've got 3 electrons. So if the electron decides to occupy the px orbital, so the electron and its negative charge is now, the electron is buzzing around in this space over here. So that area is already occupied. So if there's another electron coming around, why would that electron enter the px? It's going to avoid that. There's going to be repulsion. It would prefer the empty space that's over here. So the next electron would actually occupy the py orbital. And if there's a third electron, the third electron is going to stay away from the px and the py because there's already an electron over there. It's going to occupy the empty space that's available on the z-axis. So the third electron would occupy, its negative charge is going to get distributed on the pz. So initially they will all prefer their own independent spaces. It's like people, it's like if you have a house and the people entering, you're going to prefer your own room. Like it's only if you have more people arriving, then there's a problem. So the electrons would prefer in a subshell, because all 3 subshells are exactly, all 3 orbitals, sorry, in this subshell, in this p subshell, they're exactly identical. The electron doesn't care which one is the x, which one is the y, which one is the z. So the electron prefers its own area. It's the only problem starts when you have more than 3. So the first rule is that electrons occupy orbitals in a subshell in a single manner first. TK, is this clear?
Yes.
Yes.
Now, if more than 3 electrons come in, now there's an issue, because now there should be 2 electrons in an orbital. So if you have, let's say, a fluorine atom, so fluorine has a total of 9 electrons. So 9 electrons would be 1s2, 2s2. Now we've got 5 electrons in the 2p. So that means the 3 orbitals, you've got no choice anymore, because initially 5 electrons, each electron would prefer its own space, its own orbital, but you've got 5. So now they're going to get paired. So they start pairing up after this, and then they're going to pair up. So then you'll have 2 electrons in 2 of the orbitals, and one of the orbital is going to be half filled. So this is called an unpaired orbital. I mean, that's the terminology that's used. This one is unpaired, and they're going to be two paired. A lot of questions come on this, especially related to electronic. They ask you to count a lot of paired and unpaired orbitals. So, which is why you should know how an incomplete subshell is going to be filled. So, is this point clear? All clear?
Yes.
Yes. So I have a question.
Yeah.
So do we just generally start filling from the left, or could we have started filling from
So now in reality, it could be. I mean, I told you that all three are identical, right? I mean, the electron doesn't know which one. I mean, I call this the X, right? It could be anyone could be the X, right? Do you get my point?
Yes. Yeah.
So the point is, so conventionally speaking, so that everyone follows a certain rule, they use the X is filled first, then the Y, then the Z. Like you start from the left, then the second one, then the right one. In reality, it could be anything.
Yeah. Okay.
Okay, but the convention is, the first one is the PX, then you have the PY, then you have the PZ. So you follow that convention, and that's actually that's the way you label the axis as well. Like if you see an electron in the X, let's say in an electron microscope, you see an electron buzzing around. The first one that's getting filled, you call it the X. The second one that's getting filled up, that you call it the Y. The third one, you call it the Z. So the convention is to follow from the left to the right. But it won't make a difference even if this was paired and this was unpaired. It would still kind of be the same thing. But you have to follow the convention. Now the very last thing that needs to be mentioned is the two exceptions. And they're not just two exceptions, but two main exceptions to the Aufbau principle. The reason I'm calling them the main exception is because when you're dealing with chemistry, usually you're not talking about all the elements in the periodic table, because most elements in the periodic table, you're never going to deal with them, at least on planet Earth. They're so rare that they would hardly exist on planet Earth. So which is why we don't care about their chemistry. We don't care about the electronic configurations. For example, if you look at francium, there's just I think 2 grams of francium that exist on planet Earth. So the whole planet and the estimated mass is just 2 grams. So when we're dealing with chemistry, we're dealing with the elements that are abundant on planet Earth. It's usually the small atoms. It's usually the hydrogen, the oxygen, and atoms that are smaller in mass. So the main exceptions, you have more than one, but these are the common ones that you see in the everyday reactions that you're going to meet. The first one is copper, and the main exception is to the Aufbau principle. That there are some elements that are not going to follow the table exactly. They're going to somewhat follow the table, but the arrangement of the electrons is not going to be exactly the way the Aufbau principle describes. And those two elements are copper and chromium. So copper has 29 electrons. Now, this is one thing that you have to remember. You have to remember the electronic configuration of copper, basically. So if I follow the Aufbau principle, if I follow those arrows that I showed, copper's electronic configuration is going to be 1s2, 2s2, then 2p6, then 3s2. I can follow the arrows. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d9. That's 29 electrons. So you're going to end over here. This arrow, at the start of this arrow, that's where the electronic configuration is going to end. So let's write that down. It's going to be 3s2, 3p6, 4s2, and 3d9. And I also told you to arrange them according to the subshells. So it's better to have the 4s on the outside because that's the higher energy one. So I previously told you that the offer principle doesn't always order them properly. So make sure you give them the order yourself. Don't change the electronic configuration, just reorder them. That's it. Now the thing is that this is according to the Aufbau principle. But the reality is copper is actually slightly different, just very slightly different. It's not 3d9 4s2, it's actually 3d10 and 4s1. That's it. I mean, that's the actual electronic configuration of copper. So this is something that you just have to remember. There could be a number of reasons for that. There are a number of factors that are involved in this. What you just should remember is, I mean, this only applies to copper. So for copper, completely filled D subshell has a more stable state. So you just have to remember this for copper. And the same applies for chromium as well. Chromium has 24 electrons. So if you go on about writing the electronic configuration, it's going to be 1s2, 2s2, 2p6. Then you have 3p6, 4s2, and you'll be left with 4 electrons, and that's 3d4. First thing, just reorder them. The 4s should be on the outside. The 3d should be on the inside. And once you've done with that, coppers, this is according to the Aufbau principle, but the actual electronic configuration is, it's not actually 3d4, it's actually 3d5 and 4s1. So this is the actual electronic configuration. So you get a lot of questions on these two exceptions, and you should remember this. So it's not exactly following the Aufbau principle. The electronic configuration is slightly different. So, and there are a number of reasons, number of factors in play. No one has actually ever figured out why this is exactly. I mean, they haven't really figured out or pinpointed exactly why this is happening, but this is what the fact is. So you just got to remember this as an exception. Is that clear?
Yes.
So everyone, is this clear? Yes or no?
Yes, sir, it's fine.
Yes.
So now we're done with when you're dealing with electronic configurations, we're basically done with the whole, like all the factors related to electronic configurations. Now, the thing is, it takes now there's one thing, you've got to make strategies when you're doing past paper questions. You've got, and the first number one thing about AS is you've got to be very quick. The Aufbau principle is a very lazy principle. It's like it consumes a lot of time. Chromium just has 24 electrons. Like if you have iodine, that's a waste of a lot of time. Like iodine is 53 electrons. If there's a question coming on iodine, and I want to figure out the electronic configuration of iodine, it's going to take me a long time to actually figuring out electronic configuration of iodine. It's 53 electrons. I don't even know where it's going to end. I'm going to try and write this. I mean, like as quickly as possible, 2s2, but it's a waste of time. 2p6, 3s2, 3p6, and what 4s2, 3d10. Now I'm not sure what's coming after. I need to. Now during the paper, I would have to actually. I mean, for iodine, I would actually have to do this. So 3d10, then it's going to be 4p5, I think. 4p5, 5s2, 4d. So let me just do that over there. So 3d10. then it's going to be 4p. I guess it's just going to be 4p5, I think. Let me just check. Would that give me 53 electrons? Up till this point, it's going to be. So it's basically taking a lot of time. It's up till this, it's 30 electrons. Then that's 35. So I would have to move further from this. So 35. So let's continue. We have to reach 53. So I'm at 4p. So 4p is going to be full, 4p6. So that's 36. After 4p, there's going to be 5s2. After that, it's going to be 4d10. And hopefully it's going to be 5p5. So let's go back. So if I follow the order, it's going to be 4p6 was 36. This is 38, 48, and 5. That's 53. So I end up over here, and I can kind of rearrange stuff. The 5s must be on the outside. So the point is, the off-ball principle is a waste of time. I mean, for smaller atoms, it's not. But as soon as the size of the atom increases, it's a big waste of time. And you don't even need the entire electronic configuration of atoms. What you're only interested in most of the time is just the outermost. Because when you have an atom, the inner atoms are not really doing much. I mean, the inner atoms are not involved in interaction with other atoms. The inner atoms are too close to the nucleus that they are practically hidden from the outside. So it's the electrons that are on the outside that are actually playing the role. They are the ones that are forming covalent bonds. They're the ones that are forming ionic bonds. They're the ones that are getting lost. If an electron is gained, the electron would be gained in the outer shells. So we're only interested in the outer shells. That's so let me write that. So we don't care about the entire electronic configuration of the atom. So, I mean, is the point clear?
Yes.
So first thing, for bigger atoms, the off-ball principle is a waste of time. So how can you make this thing quicker? Like, how can you speed this thing up? So one way to speed this up is the shortcuts about writing electronic configuration, and specifically we're interested in the outer shell. And that is, you've got group numbers, and you also have shell numbers. So first thing, if you look at group numbers, I mean, you don't remember you have to draw the table and then you have to write all of this. That's too time consuming. So first information that you're going to derive from group numbers. So if there's any atom that's in group 1, just remember its outer subshell is going to be S and it's going to have 1 electron in it. Think of any atom in group 1, it's going to be the same case. Any atom that's in group 2, its outer subshell is going to be S with 2 electrons in it. Any atom that's in group 3, its outer subshell is going to have an S with 2 electrons. I mean, I'm not writing the shell number over here. I'm not writing the number over here. We'll discuss that later. So it's going to be S2 and P1. There's going to be 2 electrons in the S subshell and 1 electron in the P. Remember, group 3 is now actually called group 13. So we'll use that terminology. Otherwise, 3 and 13 are the same one. Then you have group 14 or group 4. That's going to be S2 and P2. And then you have group 16. So that is going to be S2 and, sorry, not 16, 15. Or group 5, S2 and P3. And group followed by group 16, that's going to be S2 and P4. And I'll explain this again by writing electronic configuration. So followed by group 17, that's going to be S2 and P5. And the last one is group 18, which is the noble gases, or group 0, the old group 0, or group 8. That's S2 and P6. So iodine was a group 17 or group 7 or a halogen. That was what iodine was. So its outer shell, and remember this is we're referring to the outer shell. The outer shell electronic configuration is going to be this. So when I write this, I'm actually talking about the outer shell. So iodine was group 17. So it's supposed to be S2 and P5. So you can have a look. I mean, we spent all that time only to figure out that we could have known that directly by just looking at the group number. It's just S2N and P5. That's it. I mean, forget the shell number. I'm going to come to the shell number later, the energy level, but it's S2 and P5. So we could have figured that thing right away. Any element that's in, if we go and have a look at all the previous electronic configurations, I'm not going to write transition metals. Fluorine is group 17 as well, so its outer shell is S2N. P5, it's still S2 and P5. Nitrogen was group 5 or group 15, so it's S2 and P3. You can have a look at the table. So group 15 is S2 and P3. So you could have just figured that out right away. Why waste your time on the offer principle? Is this point clear?
Yeah.
Yes.
So then there's the other thing. How do you figure out the shell number? Like the number, is it going to be 4s2 or I mean, like if I have argon, so argon is argon is what's I think it's 18. So if I follow the offer principle, it's going to be 1s2, 2s2, 2p6, and then I'm going to have 3s2 and 3p6, right? That's 18, I think. So I could have known this all, I mean, without even writing the electronic configuration. So now the question is, how do I figure out, is there going to be the number 3 going with them, or number 2, or the energy level? So that the shell number can be determined by the period number. The period number, which are the rows in the periodic table, that tells you the shell number. So the period number is equal to the shell number. It's equal to the shell number. That's it. So you could have just opened a periodic table. Like if I have, let me just open any random periodic table. Let's go with the Wolf's periodic table just a second. How do I? Yep, this one. So argon is period number 3. Remember, the first period has very few elements, just 2 of them. Then you have the second period, then you have the third period. So argon is in the third period. So that would have given you 3 over here. So it's going to be 3s2, 3p6 for argon. Pick any other element like in group 16. If I pick any element in group 16, which is group 6, if I pick Te, which I think is tellurium, the electronic configuration of tellurium is going to be S2 and P4. I think for group 16, it is S2, P4. It is S2, P4. And the shell number is going to be, this is period number 1, 2, 3, 4, 5. So it's going to be 5s2 and 5p4. So that is what the electronic configuration. Yes, Maneep.
Sir, I just wanted to confirm, hydrogen belongs in period 1, but it doesn't belong in any group, right?
Yes, exactly. It doesn't belong to any group. The reason is that it can actually kind of do both. I mean, it's it's a metal and kind of a non-metal both at the same time. Like
All
it can,
right. Okay.
I mean, it's usually non-metallic, but it can form positive ions as well. So it's kind of, hydrogen is kind of like a weird element. It's very common. It's one of the most abundant elements in the universe. The thing is, it forms a positive ion like a metal, but it forms covalent compounds like a non-metal. So it's kind of something that's in between, which is why it's kind of placed somewhere in a no-go area, somewhere in between. These are non-metals, these are metals on the left side. Is that clear?
Yes, sir. Thank you.
I said, so is this clear, the quick way of writing electronic configurations, right? Is this clear?
Yes.
I said, but so let's try this for chlorine, right? What is chlorine's electronic configuration, like without using the Aufbau principle? So chlorine is S2P5, so that's fine. It's S2 and P5. What shell number would they have? Chlorine is period 3, so it's going to be 3s2. So it's going to be 3s2 and 3p5, right? I said, now this electronic configuration kind of looks incomplete. I mean, although we are only interested in this outer shell electronic configuration, but it's obviously incomplete because you haven't written anything else. Like, what about the inner shells? Like, so just to sort of cater to the completeness, what they do is, this is chlorine. You go back, and how many electrons are left? Like 17 electrons. So 7 electrons are in the outer shell. So how many electrons are left? 10 electrons, right? So we need to figure out what those 10 electrons are doing, right? Because we didn't write that. We didn't write the whole electronic configuration. So the easier way to do this is, what is the electronic configuration of 10 electrons? That's going to be like neon, because neon has 10 electrons. So what you're going to do is, you're going to just write neon. You use a noble gas as just to complete the electronic configuration. So let me just explain this one more time. The actual electronic configuration according to the Aufbau principle was 1s2, 2s2, 2p6. Sorry, yes, 3s2 and 3p5. We directly figured out that the electronic configuration was this, right? We directly figured out that by just using this table and the period number, we were able to figure out without writing the whole electronic configuration. But just to cover for the remaining part, like, what do we do with this part? Like, we don't write, we don't want to know the electronic configuration of the inner shells. So just to cover for that, there's 10 electrons. So we just go and have a look, like, what's 10 electrons? 10 electrons is neon. So you just write neon over there, and that would give you the electronic. So that's another way of writing electronic configurations. Did you get this point?
Yeah.
Okay, so noble gases are often used to cover for the inner shells. Like, we don't care about the inner shells. So you just put a noble gas if there are 20 electrons, if there are 18 electrons. So for example, let's do it for calcium. Calcium, if I want to write the electronic configuration of calcium, what I'm going to do is, let's take calcium, and calcium has 40 electrons in total. Now, by just looking at calcium in the periodic table, I know it's in group number 2. So that is, it's going to be S2, and it's period number 4. So it's 1, 2, 3, 4. So it's period number 4. So calcium is just going to be.
Sir, doesn't calcium have 20?
It has 20. You're right. Let me correct this. So calcium has 20. So 40 is the atomic mass. Sorry. I said, so we know it's in group 2. So just look at the table. It's S2. and it's in period number 4. So it's going to be 4s2. That's the outer shell. We're done with that. What about the remaining 38 electrons? Sorry, what about the remaining 18 electrons? What do we do with that? The inner shell.
Argon.
So that's argon. That's 18 is argon. So I'm just going to, I don't care about the inner shell. So I just write argon next to it. And I'm done with calcium's electronic configuration without wasting any time. So a lot of times you use that. Now the things kind of become trickier when you go for when you try to do the same thing with elements like bromine. Like if you go for bromine, you would have to. I mean, I would have to talk about bromine and transition metals probably in the next class because that's going to take some time. So we'll talk. We haven't talked about transition metals over here. So up till 20 elements, everything things would become slightly complicated after 20 transition elements come in. So there's some additional information that needs to be done. I mean, the shortcuts that you're going to use, there would be some additional knowledge that needs to be added to write electronic configurations of elements that are bigger than 20. So we'll probably cover that in the next class. Otherwise, we're almost done with this. So I'll just do that probably in the next class then. Any questions? All clear? Fatma, Rima, everything clear? Done? Munib, Omar?
Yes, sir.
Yeah.
Yes.
Yes.
Okay, then let's continue. Tomorrow I won't be taking class. It's Monday, Tuesday, and Thursday, Friday. Not Wednesday. Okay.
Yeah, okay.
I'll send you some
All right, sir.
questions to practice.
Okay.
Take care.
Okay. Thank you, sir.
No.
Okay, assalamualaikum, sir.
Assalamualaikum.